Hello, community. There are a lot of questions. Hey, how should I start with AI agents? And what is the latest technology with agents? Well, let's have a look. Navigating digital knowledge manifold with agents. Now, if you're beginning, you say, hey, yeah, it's the true nature of an AI agent that we're interested. And maybe you say, maybe it's the true nature of an AI agent, and both of you are right. So, 8 hours ago, I published here that in the last 23 days, we had 520 scientific preprints only on AI agents. So this means at the end of January 25, we will have in 1 month more than 700 scientific publications on agents. And you can now ask, hey, what if I would like to build an AI agent today? What is important to integrate? What configuration is high risk? Or what minimal configuration I should go for? What do I have to integrate? Let's have a look at this. Now, the challenge today of creating truly intelligent AI agent, and I'm not talking about agents that are rule-based, I'm talking about agents that have a vision language model or a large language model at their heart. So, truly intelligent AI agent lie in their capacity to navigate complex and dynamic digital knowledge manifolds. Whatever you know about virtual worlds, about digital twins, this is what we're looking for. Let's say we have the data on data manifolds, and they represent vast interconnected data and interconnection spaces that are normally ill-defined and require our agent to go beyond the pre-programmed and pre-trained behavior. And here you immediately see why it is so important to go with intelligent AI agents. I would like to give you this simple idea. You can have a classical agent, let's call it agent Z, an agent R for refined or reflective or whatever you like. So let's have a look. Our classical agent is here. Architecture is here by supervised learning. Knowledge representation is derived from expert trajectory, sequences of actions that were learned. It mimics this predefined path, but it lacks an inherent intrinsic mechanism for error detection. So therefore, they have no systematic approach to validate the coherence or adapting to novel situations. Now, if you go with R, for reflective, for reasoning, for super R, we do have a dynamic learning loop. And this is normally centered around a self-reflection and an iterative refinement or a self-learning environment. Normally, the core methodology today is Monte Carlo Tree Search, but of course, you can have, like in the latest publication by ByteDance and Fudan University, implement here a model-guided critique mechanism when my own actor network functions here as a validator of a trajectory reasoning coherence function. So, you can go from 0 really up to 100. Let's have a look at Agent R. What we have is now a function, a self-critique function, coupled with an iterative supervised fine-tuning on self-generated, so the AI generates its own revision trajectory for the reasoning task, and this forms here the base of my self-reflective learning process. As you see, we do not go with in-context learning or RAG or whatever. We really have to bring the knowledge down into the weight structure, into the weight tensor of our LLM, and therefore we do have to apply a supervised fine-tuning. Add it with PEFT, no problem at all, but you have to bring the knowledge into the parametric learning space of your LLM. 3 terms that you might be interested in. Agent R exploration via the Monte Carlo Tree Search. Classical Monte Carlo Tree Search constructed search tree. We have the classical upper confidence bound of the tree algorithm. This guides here the node selection, balancing here exploration and exploitation, where exploration simply means visiting only those less explored region, because we want to have a full swipe on the complete action space, for example. And then we have exploitation, where we know that there are some good pathway, and we work here with reward models So you know we want to follow the path that lead us to the gold at the end of the rainbow. As you see, this process generates here a diverse set of reasoning trajectories encompassing both high reward, good, and low reward outcomes. And yeah, this is the reason why we have reward functions. Second part is here the model-guided critique and revision trajectory construction. This is just to give you a feeling. We will go into detail in about 2 minutes time. What is really nice with the latest technology, they don't go here to the end of a trajectory with the Monte Carlo Tree Search, but they go step by step. Because if you are at the end, you might be in a loop. And if you have seen my last video, you saw that some of the LLMs go in a self-augmentation reasoning loop. They cannot escape. They cannot find new reasoning paths. They are locked in. And exactly to avoid this behavior, this new critique model is so beautiful because you don't wait till you have your terminal node, but you evaluate this each step of your reasoning path. I will show you how to do this. If we have these revision trajectories for a reasoning process, if they are now constructed, and I'll show you how, they are now formed by splicing here, and we have a beautiful effect of a learning error recovery. And this is what you should look for in a new agent in 2025. It should be self-learning. And then, in the end, as I told you, you have to have this self-training in your agent. You have an iterative self-training in the simplest way implemented here by supervised fine-tuning. Beautiful code available for Hugging Face for free. We have here, so the model agent R generates here revision trajectories, and then these trajectories are used to fine-tune here the actor network via supervised fine-tuning. This is it. You have a loss function, beautiful, and you have the ability in your agent to recover dynamically from erroneous actions. That's it. Let's change the perspective. If you're new to this and you say, hey, wow, can we go back a little bit more simple? Well, of course. So through the eyes of an AI agent, let's have a look at our little yin-yang agent C limitations. Agent C has a problem. The performance plateaus rapidly, and it is constrained by the incompleteness of the expert demonstration that it learned. An agent C tells us my error correction capabilities are effectively non-existent. And deviation from the predefined paths that I learned often directly lead to cascading failures and an entrapment in suboptimal loops within the dynamic data manifold. So you see, the classical agents that you have, the commercial agent and all the agents, everybody telling you and giving you examples that if you just follow their example and you become a paying member of their community, they suffer here from these limitations. The actual research and the real intelligent agents, like Agent R, they have advantages. They have a faster recovery from errors in their pathways, in the reasoning structure, if the entity loops, and they have shorter average revision length. So this is a behavior that we want to have. Plus, Agent R's ability to dynamically identify and rectify erroneous actions mid-trajectory. And here the most important term is mid-trajectory. You don't wait till the Monte Carlo tree simulation reaches here the target node, the final node, the terminal node. And then you calculate a reward signal that propagates back to the complete tree structure. No. We have it mid-trajectory, maybe almost real-time, and this is something that is completely absent in the classical behavior if you just clone your agents. So you see, if we have this ability, then we can immediately train our LLM, our agent, on this new data. So this self-training process is of utmost importance for the behavior of Agent R to continuously refine its policy by data, if you have a mathematical model. So there you have it. The first feeling, just want to give you a feeling. A comparative analysis would be a little bit too much of Agent C and Agent R, highlighting here the shift in the development of intelligent AI agents for complex digital domains. If you have only a very simple task, don't care about this video. Go with a standard agent implementation. If you just have 2 classes and you have a classification task of your agent, don't continue. This video is for more complex, for deeper reasoning digital domains and tasks. Okay, so agency, beautiful behavior cloning, while useful for initial bootstrapping, proves fundamentally limited in its capacity or the dynamic error correction or adaptation. Think about quantum error corrections. And the new beautiful Agent R, with its self-reflective learning framework, incorporates now 3 elements: Monte Carlo Tree Search driven exploration, an intrinsic model-guided critique function, and a self-learning iterative supervised fine-tuning on the revision trajectories. Isn't this beautiful? Or, if you want to call it here in more classical terms, intrinsic mechanisms for self-monitoring, error detection, and a dynamic policy revision of your agent. Now let's look at a little bit deeper in the Agent R flow description. And we go here with the definition from ByteDance and Fudan University here, 2 simple phases: model-guided reflection trajectory generation and the iterative self-training. And in this moment you say, my great, hey, but wait, don't we need code? And code needs a mathematical framework to apply to, no? Code is mathematics. So in what mathematical framework are we working? In what mathematical framework are you thinking? What you present here to us? Well, classical. I go with the simplest one. Partial observable Markov decision processes. This is, we have for hundreds of years in physics, in mathematics, and we apply the same here in computer science. So we have here a classical mathematical framework used to model decision-making in situation where an agent interacts with environment but cannot directly observe the complete state of this environment. So our Agent R uses here exactly this partial observable Markov decision process formulation to frame the task of training the language agents in our interactive environments. Now maybe you have seen this notation here. So just to be clear, even for beginners, hello, welcome to the channel. We have an instruction space, a state space, an action space, an observation space, a transition function, and a reward function. And all of this is an established mathematical theory that interplays and delivers beautiful results. I give you here now an explanation you see on your screen in the context of Agent R of the specific spaces. Let's go with the action space and you immediately get it. Now there are multiple, if you can call it benchmarks. You have, I don't know if you know this web shop here, for example, or SciWorld. They are kind of tests you can perform to get an idea how good you are. And you see here simple examples if you are into this. Or if you just think, hey, OpenAI's operator, you know? Think about here, this would be an action space where the OpenAI agents are now able in the action space provided by your computer. If you upload here, you give access to your computer, OpenAI agents called the operator will have access to your functionality on your computer. This is the explanation of the observation space. This here is in the context of Agent R, the transition function, and of course we need a reward function with the learning reflection. Okay, so I think we're ready now. Yeah, let's do this. Phase 1, let's build this. Now, next step. We have Monte Carlo Tree Search exploration phase. So, starting from an initial state, the Monte Carlo Tree Search is initiated to explore the complete action space for our agent. So for each node in the tree, we have here the upper confidence bound for the tree's algorithm, guides here the selection of the child node to expand. Beautiful. And then we have here our actor model pi sub theta. This generates now the actions. You know, classical Monte Carlo Tree Search, we have multiple rollouts defined by the parameter k, from newly added node to a terminal state or a predefined maximum depth. And during the rollout, we have here, if we start here in the initialization phase, a default rollout policy to simulate here the future actions. Then, and this is the beauty, of completed for a set of numbers, the generated trajectories are now evaluated based on their final reward. This is the classical what we know. We can have a specific threshold we call beta to distinguish between the good trajectory, whatever they are in your system, and the bad trajectory that are above or below beta. Couldn't be easier, you see? But now comes the beauty. Careful. The model-guided critique is nice, but watch what is happening. It is going now step by step. This is the new idea. So for each bad trajectory that is below the parameter beta, the current actor model or policy is prompted to act now as a verifier. You have the complete history log of the trajectory, beautiful. And then the actor model is asked to judge whether the current action is good, bad, or neutral, or uncertain, or whatever you like. So plus, minus, 0. And based on the feedback, the first error step within the bad trajectory is identified. So if you have a complex reasoning process, or you have a robot, and the robot enters a room and the task is to open the fridge, the robot has to orient in the room, find the fridge, identify the object, identify the path from its current position to the fridge, aware of all the obstacles in its path, find other path with no obstacles, and then you evaluate every step. And if you see, hey, there I made in my first draft of the reasoning an error, this is your first error step. At this point in the tree structure, you put a flag and you say, hey, here something starts to go wrong. You don't wait till you crash into the wall, but you say, hey, here something happened and I have to find from here a different solution. Now to the beautiful idea of splicing. How do we construct our revision trajectories? Now, remember we have the bad trajectories and we have the good trajectories. So for each bad trajectory in its identified first error step, let's say it's t, a corresponding good trajectory is also selected that shares here the same parent node in the tree structure up to the step t. So how we do the splicing? Now it's easy. The initial segment of the bad trajectory, so this means from step 1 to t, is chosen. Then we have this revision signal, could be a textual prompt indicating the reflection on this error here, is inserted here at the step t plus 1, and the subsequent segment of the good trajectory from the step t plus 1 to its terminal point is now spliced. So you see, we have now beautifully constructed a revision trajectory. And this splicing now creates here a training example that we are looking for, because it explicitly demonstrates here the error correction. So therefore it guides here our LLM from an erroneous path to the correct one. So the LLM clearly identifies here when things start to go wrong, and the LLM is not going in a loop. It is not crashing against the wall, if you think about the robotic example, and then the robot gets here the reward function. Oh, this is a wall, it hurts. No, we don't wait till the end, but we have it here immediately here with our revision trajectory construction methodology. So, now we have those trajectories. And now starts the beauty of supervised fine-tuning. So, actor model is now fine-tuned using a particular loss function. And this loss function has 3 terms. No, of course. We have the good trajectory loss function, maximizes here the log likelihood of a good trajectory to reinforce the good optimal behavior that we are searching for. Then we have the revision trajectory loss, maximizes here the log likelihood of the revision trajectories, tau, specifically focus on the predicting the revision signal and the subsequent corrected action from the step t+1 onwards. And this is here the crucial term for the learning, the error recovery phase. So if we have, I don't know, what we saw, Google LLMs went into a reasoning loop and was not able to escape. This is the term in the loss function that will catapult here our LLM out of this loss loop. And then we have a general data set. Loss is optional to improve generalization for a particular domain. And you're not going to believe it, this is now an iterative process. So after the supervised fine-tuning, we have a newly trained actor model, and we start with the phase 1.1 again. Iterative cycle of phase 1, trajectory generation, and revision data construction, and phase 2, supervised fine-tuning, is repeated for predefined number of iterations. And this self-learning is what I would recommend that you have in your new AI agent. Because in each iteration here, the agent uses a progressively improved policy to generate new and potentially more informative revision trajectories, because it knows where its action failed and therefore has to find or substitute with better actions if they utilize here the policy. And all of these leads here to continuous self-improvement in the error correction and the overall task performance. So you have to invest a little bit more here in the training of this agent, but the real-world application are real nice because you can make sure almost that your LLM, your agent, will not enter into reasoning loops and never recover from them. Terms, yeah, what I found. Some of your question, yeah. Unfortunately, people use a lot of terminology for the identical objects. Now, do not get confused by all this different jargon, these different technical terms, because, you know, there's a good chance that they all reference the same object. Have a look here. If they talk about an actor model or an actor critique methodology in reinforcement learning, if you read the definition then of this, you notice this is precisely the definition of a policy in reinforcement learning. Because a policy in AI is a mapping from the states, and this means from the observation or the history of the system, to the actions or the probability distribution over specified actions. So actor model is really, really deeply related to the policy of the system. Then you see policy as action selection strategy. Now, the policy model or the actor model, and don't worry, this is the same, embodies here the agent's strategy for interacting with the environments. It simply detects how the agent behaves and makes its decisions. This is true for robotic, this is true for reasoning. So in the agent or literature, you will find here not the policy, but you will find the actor model as a technical term. But the actor model will be denoted here in the mathematical form as pi theta, which is, in the original literature, the policy. Policy parameterized by theta defines the agent policy. So, if you hear the solution to all of this, the policy model is the actor model, is the action generating mechanism, is equal to the action agent strategy, and is, in the mathematical notation, pi sub theta. So you see, sometimes people refer to those things, and you can see that sometimes people are not really sure, and sometimes they have a little bit of a mix-up of here the complete technical terms, but never mind. If you understand the main idea of the theory, of the new methodology, you immediately understand that policy model and actor model and the agent strategy and pi are the same thing. Now that I've told you everything about Agent R, it's time that I show you here this beautiful paper. So you have here the paper, January 20, 2025, Agent R, training language model agents to reflect via iterative self-training. Fudan University and ByteDance. Oh, ByteDance Seed. Oh, interesting. Here you have the code. GitHub, this is your link. Explore it, enjoy it. And now this is the perfect time if you want to read the paper. And now you immediately understand the different terms and why we built this formula in the way you see it here. And I hope that this video provided you the insights of the main idea. Now, of course, I have to give you here the performance data, the benchmark data, and as I told you here, WebShop or Cyberworld or TextCraft or whatever, here you have the different LLMs, here you have your different agent, and of course, here in the last line, you have your agent R. And as you can see, as expected, for those selected benchmark here, they have here the best performance overall. So if you're interested to learn here about AI agents, their main element, what should be included in a minimal configuration, I would go for a self-reflective, self-learning methodology, because then your agent will adapt and will continue to learn if you give it more and more challenging tasks and more complex reasoning data. So therefore, I hope you enjoyed this video. To navigate digital knowledge manifold wherever you encounter them, the minimal configuration for agents. And if you're interested in my next video, hey, why not subscribe?